Welcome to Lesson 1 of Unit 5, which is all about trigonometry. This first lesson will be a review of trigonometry from grade 10 with a few new concepts. We're going to begin by evaluating the trigonometric ratios, often known as SOHCAHTOA, and something new this lesson will be to look at their reciprocals. Let's get started. First, to review, please recall that in right-angled triangles, the primary trigonometric ratios, often known as the SOHCAHTOA acronym, are shown below. Given a right-angled triangle, the side opposite the 90-degree angle, which is right here, is always labeled as the hypotenuse. Then, the labels of the other two sides are relative to the angle that you're talking about. For instance, if we label angle A with the Greek letter alpha, shown over here, that's the Greek letter alpha, the side across from that angle is referred to as the opposite side, and the side in contact with that angle, which isn't the hypotenuse, is referred to as the adjacent side. And with that being said, your SOHCAHTOA ratios are shown to the side. Sine of the angle is the ratio of the opposite side to the adjacent. The sine of an angle is the ratio of the opposite side to the hypotenuse. The cosine of an angle is equivalent to the ratio of the adjacent side to the hypotenuse. And finally, the tangent of an angle is equivalent to the ratio of the opposite side to the adjacent side. Once again, these only work for right-angled triangles, and in any right-angled triangle, you can always use the Pythagorean theorem, which is shown below. I've labeled it as h squared equals a squared plus b squared. I'm just being consistent with the labels in the diagram, but you probably more commonly remember it as c squared equals a squared plus b squared. Let's practice an example 1. For the right-angled triangle shown, we want to determine the length of side x. So consider that we're given angle y, which is equivalent to 67 degrees. Relative to the angle provided, x would represent the adjacent side, and the 18 millimeters is the hypotenuse because it's opposite the 90-degree angle. Which of the three ratios has a and h? It would be the cosine ratio. So cosine of 67 degrees is equal to adjacent over hypotenuse. Let's substitute. Cosine of 67 degrees is equal to x. That's the variable representing the adjacent side. And the hypotenuse in this example is 18. Now to solve for x, you have to use SAMDEB. So on the right side of the equation, we're dividing x by 18. You undo that operation by multiplying both sides of the equation by 18. If it helps you, you can put brackets around the cosine 67 degrees. That should remind you that that operation will return one number, and then you have to multiply that number by 18. So please take a moment to do this on your calculator. One important thing, please check to make sure that your calculator is in degree mode. If not, you're not going to get the same answer. I didn't specify how many decimal places to round to. I'd say 1 or 2 is fine. So the correct answer to 2 decimal places is approximately 7.03. If you did not get that number, likely your calculator is in the incorrect degree mode. Okay, let's do another one. In this case, we're asked to determine angle theta. So relative to angle theta, we're given the opposite side and the hypotenuse. The ratio that has the opposite and hypotenuse is sine. So sine of angle theta is equivalent to opposite over hypotenuse. Go ahead and substitute. And now you have to find angle theta. You do this by performing the inverse operation of sine. So what we do is take the inverse sine of both sides, that's sine with a -1 as a superscript. And on your calculator, usually you do this by pressing the second function button followed by sine, or perhaps the shift button followed by sine. Once again, I didn't specify how many decimal places to round it to. I'd say 1 or 2 is sufficient. So therefore, angle theta should be equivalent to approximately 66.4 degrees. So please make sure you got that answer. If you didn't, once again, your calculator is likely on the wrong degree mode. All right, that was a pretty quick review. Now we're going to move on to something new. And this is what are called the reciprocal trigonometric ratios. So in grade 10 and just now, you've learned about the 3 primary trigonometric ratios. That's sine, cos, and tan, which is where SOHCAHTOA comes from. But there are also 3 reciprocal trigonometric ratios. And these are defined as follows. They are called cosecant, designated by CSC, secant, designated by SEC, and lastly, cotangent, designated by COT. As the name would suggest, the reciprocal trigonometric ratio is just simply 1 divided by each of the ratios, and this is shown below. Cosecant is defined to be the reciprocal of the sine function. And I'll just show a little work on the side over here. If cosecant is equivalent to 1 over sine, recall that sine theta is equivalent to opposite over hypotenuse. That comes from SOHCAHTOA. So I'm going to write this as 1 divided by the ratio of opposite over hypotenuse. Please remember, anytime you divide by a fraction, you can multiply by the reciprocal. So that's 1 multiplied by hypotenuse over opposite. And anything multiplied by 1 is itself. So therefore, cosecant theta is equivalent to hypotenuse divided by the opposite side. Essentially, these 3 new ratios are just the reciprocals of the SOHCAHTOA formulas. So for instance, secant would be the reciprocal of cosine. Since cosine of an angle is adjacent over hypotenuse, you just take the reciprocal to get hypotenuse over adjacent. And similarly, cotangent is the reciprocal of tangent. So instead of opposite over adjacent, it's adjacent over opposite. These are 3 new ratios, and they will come back in grade 12 advanced functions, so please make sure you're familiar with them. Let's try out an example. In example 2, we're asked over here to calculate the 6 trigonometric ratios for angle A. So those 6 ratios would be the 3 we already know, sine, cos, and tan, as well as the 3 new reciprocal ratios. So here's angle A. Let's get started with one of the 3 we know. Let's say tangent. Tan of angle A is equal to opposite over adjacent. The opposite side to angle A is 9, and the adjacent is 12. So tan of angle A is 9 over 12, which reduces to 3 over 4 in lowest terms. And watch how easy this is. If you want to take now, let's say, cotangent of angle A, recall that's just the reciprocal of tan A. So flip the fraction. Instead of 3 over 4, it's equivalent to 4 over 3. And that's that. There's really nothing to these, because we're not asked to find the angle, we're looking for the ratios themselves over here. So we need to do this 4 more times for sine, cos, secant, and cosecant. I'm going to suggest you take this moment to pause the video, try it on your own, and when you're ready, click play to resume. And you're back. Let's see if you got a similar answer to mine. Let's do sine. Sine of angle A is opposite over hypotenuse. That would be 9 over 15, which reduces to 3 over 5 in lowest terms. The reciprocal of sine is cosecant, so that's CSC of angle A. And once again, we just flip the fraction. So instead of 3 over 5, it's 5 over 3. Done. Last but not least would be cosine. Cosine of angle A is adjacent over hypotenuse. So that's 12 over 15, which reduces to 4 over 5. And finally, secant of angle A is just the reciprocal of cosine, so we're going to get a ratio of 5 over 4. And there you go, everyone. Those are your 6 trigonometric ratios. Let's move on. Let me take this moment to remind you of some terminology from grade 10, angle of elevation and angle of depression. So the angle of elevation or inclination is defined to be the angle formed by a horizontal line and the line of sight to any object above the horizontal. Actually, let me make a sketch up here. So this would be an example of the angle of elevation. Here's a horizontal line. And let's say you're looking at an object up to the right over there. Then the angle between the line of sight and the horizontal. So that would be your line of sight. And the angle between the two would be the angle of elevation, which I'll label as theta. In a similar way, the angle of depression is the angle formed by the horizontal and the line of sight to any object below the horizontal. So here's your horizontal again. Imagine you're looking at an object below. Here's your line of sight. And the angle of depression would be labeled over here as theta. So please be careful here. You always have to define the angle relative to the horizontal. And with that being said, we'll try a application question. So take a moment to read it over. Try to make a sketch of the problem on your own. And when you're ready, click play to resume. All right, let's get started. So we have a camera mounted atop the roof of an apartment building that is 20 meters above the ground. So I'll just make a sketch here. Let's say this is my ground. This is my apartment building. And we've got a camera mounted atop the roof, so we'll just put it maybe up here. The camera is looking down at a car on the ground, so let's put the car over here. So I'll sketch the horizontal. The line of sight will be the line connecting the camera and the car, shown below. Notice this is going to form a 90-degree triangle. And we're given the angle of depression. In this case, it's 68 degrees. Please take note of where I put the angle of depression. It always has to be that angle between the dotted line and the line of sight. And we want to determine how far away the car is from the building. So let's label that X. And we also know the height of the building, which is 20. I'll label that right here. And now this becomes a knowledge problem. We're just trying to solve for one of the sides in a right angle triangle. I don't know if you see it or not, but there's actually a Z pattern hiding. Let me highlight it. So the Z pattern, often known as the alternate angle theorem, tells you that alternate angles are equal. So we can label this as 68 degrees as well. And now inside of the right angle triangle, we have one of the sides and one of the angles. Relative to the 68 degrees, the 20 meters would represent the opposite side, and we want x, which would be the adjacent side. So let's use tan. In this case, tan of 68 degrees is the opposite side divided by the adjacent side. We have to solve for x. Unfortunately, it's in the denominator, so we're going to have to do two steps here. First things first, let's bring x to the left side through multiplication. So x multiplied by tan 68 degrees equals 20. And then to solve for x, you divide both sides by tan of 68 degrees. In this case, the tan 68s cancel out. Remember, you treat it just like a number, which it is. And therefore, x is equal to whatever 20 divided by tan 68 is. Try it out. You should get approximately 8.1. And I guess we're all set to write a therefore statement. All right, and last but not least, I have a bit of a treat for you. Consider this a thinking problem. And this is also a bit of a sneak peek for what's to come later in the unit. So what we're being asked to do here is, for any right angle triangle, we want to prove that when you take sine theta and square it, and add that to cosine theta squared, it equals 1. So this might be the first time in a math course that you've been asked to prove something. Mathematical proofs are ways of showing that something always equals something else. It can be a bit abstract, but it's a little more formal. Here's what I'd like to challenge you to do. I want you to test this. So let me give you an example. Pick any angle you want, let's say 30 degrees. So this equation is telling us when you take the sine of 30 degrees and square it, and add that to the cosine of 30 degrees and square it, it should equal 1. So seriously, try it. I'll wait. Did you do it? Still waiting. Okay, I trust you did it. So you should have seen that it actually does equal 1. And I'm going to challenge you to try it again. Let's pick another random angle. Let's say, I don't know, how about 520 degrees? So do sine of 520 degrees, square it, and add that to the cosine of 520 degrees squared. Let's see if that equals 1. Go. And sure enough, it does. So I'm going to ask you now to pause the video, and I want you to try to break this rule. Seriously, pick any angle you want for theta. The only thing is, whatever you pick, the two angles have to be the same for the sine and cosine part. But try 0, try negative angles, try decimals, try whatever you want. Okay, give that a shot, and when you're ready, click play to resume. Okay, you're back. So I guarantee that any angle you chose, it always equaled 1. And there's a reason for that. And that's what we're going to do in this example. We're going to prove why when you take the sine of an angle, square it, and add it to the cosine of an angle squared, we're going to prove why that always equals 1. So don't mind me, I'm just going to erase this to make some room. Okay, so for any right angle triangle, we have to show this. I'm going to begin by just sketching any right angle triangle. I'm going to pick a random angle, we'll label it theta, and I'll label the sides A, B, and C. So we want to show that when you take sine theta squared and add it to cosine theta squared, that you get 1. Well, let's look at our picture and figure out what exactly sine and cosine theta are. Sine theta is equivalent to opposite over hypotenuse. In our picture, that would be b divided by c. And cosine theta is adjacent over hypotenuse, which would be a over c. We have two expressions now for sine and cosine theta. Let's plug them into the left side of the equation and see what we get. So here's the left side of the equation. Left side equals sine theta squared plus cosine theta squared. We're going to substitute the expressions for sine and cosine theta that we found. So that's b over c squared plus a over c squared. Well, let's simplify this. So we're going to square the fractions. That gives us b squared over c squared plus a squared over c squared. Can you simplify this fraction? Well, notice we have a common denominator for free. Let's go ahead and add the numerators. That's going to give us b squared plus a squared all over c squared. And at this point, we can't really simplify this anymore. We're left with b squared plus a squared all divided by c squared, and we somehow have to show that this equals 1. What can you tell me about the expression b squared plus a squared? I want you to look at the picture, look at this expression, and see if you can make the connection. I'll give you a moment to do that. Pause the video if you want, and when you're ready, click play to resume. Okay, I hope you found it. So if you looked at the picture, notice that we have a right angle triangle. And what has to be true in any right angle triangle? Well, one thing is the Pythagorean theorem. That is c squared equals a squared plus b squared. In our equation, we have b squared plus a squared, but the order of addition doesn't matter. So you can replace b squared plus a squared with c squared because that follows from the Pythagorean theorem. And now this expression becomes c squared divided by c squared. What happens? Well, you're dividing the same thing by the same thing, so they cancel out, which reduces to 1. Amazing, right? And therefore, we have proven that sine of angle theta squared plus cosine of angle theta squared equals 1. Notice this is a proof because we didn't do it for specific numbers. We showed that for any right angle triangle with sides A, B, and C, it'll always work. That's why this was a proof, because you showed it works generally in all cases, whereas before we were testing it using specific numbers. That would be an example, not a mathematical proof. Well, I hope you found that interesting. We're going to get into more of this stuff later in the unit. But with that being said, we're all done our first lesson, so here's some recommended homework from the textbook. Please try it out. If you have any questions, don't hesitate to let me know. And other than that, I'll see you in the next video. Take care.